We're now going to use each of the approximation techniques that we've learned to find the area bounded by the sine of x and the x-axis between 0 and pi. And we should expect that all of these answers will be kind of in the same ballpark because we're approximating the same thing each and every time. But there may be some subtle differences between the values. Some are going to be a little bit more precise than others. One thing that might be useful in this problem, since we're going to use 4 subintervals, is we might want to go ahead and make a table of values of x and sine of x. And if we're starting at 0 and going to pi, and we're dividing that up into 4 subintervals, then this graph that I have displayed here is convenient because it shows us what each of the 5 x values we need to create those 4 subintervals, namely 0, pi over 4, pi over 2, 3 pi over 4, and pi. And these are very easy values to calculate the sine of them. So sine of 0 is 0, then we have root 2 over 2, then we get to our maximum of 1, then we go back down to root 2 over 2, and then back down to 0. So these values may come in handy for some of these methods. For example, with the RAM, we're going to take our delta x value. Well, our delta x value is going to be the same for each of these, right? The distance between each one of these is the same. This distance right here is pi over 4. Same as this distance right here, same as this distance right here, same as this distance right here, for equal subintervals. So delta x, or pi over 4, is going to be the base of each one of these rectangles, and we're going to use the right endpoint. So we're going to use pi over 4, pi over 2, 3 pi over 4, and 0 for our heights of our rectangles. So that's going to be these 4 y values. So we'll have root 2 over 2, we'll have 1, we'll have root 2 over 2, and we'll have 0. So we can add things up here. So we've got pi over 4 times some stuff. Well, root 2 over 2 plus root 2 over 2 is root 2, and 1 plus 0 is 1. So we can say that this is, well, we could leave this as the final answer, or if we want to, we can write it as a single fraction, putting that in parentheses, and then the pi outside of the parentheses, and we end up with an approximation for the area under the curve. Now, if we try to do the same thing with LRAM, the width is the same. It's delta x is still pi over 4. But we're not going to use the right endpoints. We're going to use the left endpoint. So we're going to start with 0. Then we're going to use pi over 4. We're going to have pi over 2. We're going to have 3 pi over 4. But we're not going to use that last bit, right? So we're going to use this, 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 and this y value. All right, well, you might see what's happening here. We end up with exactly the same values in our parentheses. The 0 is just the beginning instead of at the end. So this doesn't normally happen, right? Normally the LRAM and the RRAM give us different values, but just due to the nature of the symmetry of this problem, we end up getting the exact same answer. All right, moving on to MRAM. Well, we're still using the rectangles whose base down there, the bottom part, is pi over 4. But this time, we aren't going to use 0 to find the height of our rectangle. We're not going to use pi over 4 to find the height of our rectangle. We're going to use smack dab in the middle, the midpoint, and that's going to be pi over 8. And that pi over 8 is not the height. The pi over 8 is the x value that we'll use to determine the height. So that height right there, well, that's going to be the sine of pi over 8. And then we'll do the same thing here to find that height of the next rectangle is going to be sine of 3 pi over 8. And we'll do the same thing again to get the next rectangle's height is sine of 5 pi over 8. And then we finally have our last rectangle's height is going to be at 7 pi over 8. Now, if you are feeling very brave, then you can go ahead and pull out that half-angle identity that you learned last year in pre-calculus, and you can evaluate this. I'm not going to do that because I want to move on to the rest of my life. But it's not a bad idea to do if you have the time and the interest. All right, so the trapezoidal method. The trapezoidal rule is going to start off with the 0 and then go to the 4. We'll switch colors here. We'll use light blue. All right. Try to use light blue. So we're going to take 0 and pi over 4, these two heights, and we're going to draw a line connecting them, right? So that's going to be our first, quote, trapezoid. It's actually a triangle because the first height is 0. But when we do b minus a over n divided by 2, this is going to be pi over 4 divided by 2, or pi over 8. And we have f of 0, which is 0. We have f of 1, which is root 2 over 2, but I have 2 of those, right? And then I'm going to get pi over 2 is going to give us a 1, but we have 2 of those. And then 3 pi over 4 is going to give us root 2 over 2, but we have, you guessed it, 2 of those. And then we go back down to our endpoint at a height of 0, and we only have 1 of those. When we try to simplify this out, we get root 2 here, and we get root 2 here. When we add those up, we get 2 root 2. The zeros go away, of course, so we have pi over 8 times 2 root 2 plus 2. 2 root 2 plus 2. And some of you might be noticing that if we factor out a 2 and reduce that with the 8 in the denominator, we end up with root 2 plus 1 times pi over 4. Well, this is a little bit surprising. We got the same answer 3 times. Until you remember that there is a relationship between RRAM, LRAM, and the trapezoidal rule. And if you remember that relationship, then perhaps it's not at all surprising that all 3 of them are the same. Anyway, we'll go ahead and give this last method a try, this Simpson's rule method. We'll need a new color for that. And this time, remember, we're not using straight lines to approximate, but we're using parabolas, and the parabola is going to go through the first point, the second point, and the third point. That first parabola is, and then our second parabola is going to go through this point, and this point. Okay, so we're only going to have 2 different parabolas, but when we apply that formula, let's see, we have b minus a over 3 this time, so 3n rather, b minus a over 3n, so that b minus a is pi, and if n is 4, we have 3 times 4, which is 12. And we'll use these same values of 0, root 2 over 2, 1, root 2 over 2, and 0, but we'll change our coefficients. Remember that the first coefficient is 1, and then we use 4, and then we use 2, and then we use 4, and then we keep on going back and forth between 4 and 2 until we get to our last 4, which is the second to last term, and then we go to coefficient of 1 for our last y value. Okay, so this is, again, Simpson's rule, and we end up with 2 root 2 plus another 2 root 2 is 4 root 2 inside the parentheses there. And then we also have a plus 2, plus 0, plus 0. And then if we divide both of these by 2 and cancel it out with one of the factors of 2 on the bottom, we get pi over 6 times 2 root 2 plus 1. Or if you want to write it in fraction form, we can put that 2 root 2 plus 1 times pi in the numerator and put the 6 in the denominator. Now, one thing we haven't learned yet is how to find the exact area of these trig functions. We'll get there pretty soon, but if I were to tell you that the exact area of this definite integral was 2, and then you could then pull out your calculator and compare each one of these answers to 2, and it might be a fun activity to try to figure out which one of these is the most accurate. Make a prediction, and then see if your prediction is right. Remember, there are only 3 values to check because our answers for A, B, and D were all the same. So those are all of equal accuracy, whether that's good accuracy or bad accuracy. You can determine that yourself.